Alright, in this video tutorial we're going to talk about analysis of variance or Anova, and we will learn the concepts of Anova using a real-world example in R, and then we will interpret the results. So Anova is an extension to t-test and is used when you would like to compare the means of two or more populations. So notice that this is an inferential statistics because based on the sample data, we want to make inference about the population. The null hypothesis in the Anova states that the means of all of the population groups are equal. So notice that we have some samples and we want to make inference whether their population are equal or not. And the alternative hypothesis states that at least one mean of the group is different from the others. Okay. So in notational form, the null hypothesis H0 states that the mean, which is the population mean for all of the groups, are equal, and the alternative hypothesis states that at least one mean is different from the others. Assumptions of the Anova are similar to the assumption of the t-test, that the data are randomly collected and there are independent observations. We have normality assumptions that each group has approximately normal distribution, and also we have assumptions of the equality of the variance, that the variance of each group is equal to the others. And notice that assumption 2 and 3, which are normality assumption and the equal variance, can be relaxed when you have a large sample size. In this video tutorial, we're gonna use the built-in dataset available in R. So let's open up RStudio, and in RScript editor, first of all, let's make a comment that shows the purpose of this study, which is analysis of variance for plants' weights. And first of all, let's load the built-in data set. Okay, so load built-in data set in R. So we use data command and with no arguments. Okay, and if you click run, these are the freely available data set in R. And if you scroll down, we can find plant growth. Okay, so which is the results from an experiment on plant growth. So how can I use this data set? Within this, if I type the name of the data set plant growth and then run, so you can see in the data frame this data will be added. If you click on that, so we have the plant growth data set, and you can see that this data set actually has two columns or two variables. We have the weight and then we have group. So we have controls or no treatment, and we also have treatment 1 and treatment 2. So for each of the, so we have three different type of plants. Okay, so the first plants, they didn't receive any treatment. The second group received a specific type of treatment, and the third group received another type of treatment. And then they measured the weight for each of the treatment. And then they want to see whether they're at the population level, whether they are equal or not. Okay, their weight is equal or not. We have 30 observation and two variables, and the variables were weight and group. And let's explore this data frame. So explore data. We use head command, head of the plant growth, to gives us the first 6 line of data, and also a summary of the variables. So we can see weight is a quantitative variable, that's why we have minimum, maximum, median, first quartile, third quartile, but group is a categorical variable. That's why we have number for each category, frequency for each category. And as this is a categorical variable, we can see the levels of this variable. Okay, so what are the levels for the categorical variable for group? So we use levels of the plant growth, and so we're gonna select we're gonna select this group, right? So we have to, from this data frame, we use $sign and then group. So we can see it has three levels, right? Control, treatment 1 and treatment 2. We're going to compare the population mean of weight for each group. Okay, remember that for more than 2 categories we no longer can use t-test. If it was only 2 categories, control and treatment 1, we could use t-test to compare their means, but here we have more than 2 categories, and that's why we should use ANOVA. I think it's a good idea if I extract these 2 variables. Extract variables, plant growth and then weight. Let's store it in object weight, and also plant growth $sign group, and store it in object group. Then run the code. Okay, so we have 3, it's a factor or categorical variables at 3 levels. In the first step, I'm going to compare the mean of weight for each of these control, treatment 1, treatment 2. Okay, so let's create a command that compare mean of weights. So we know that if I want to compare, for example, the mean of weight, so it gives us the mean of weight for all of the plants, right? But if I'm going to select only a specific plant, I have to use the square bracket for subsetting, and then here I have to mention that the group double equal to CTRL, right? And if I click run, so it gives us the mean for when I clicked run, it gave us the mean for the controls, the mean of weight for the controls. And if I repeat this for the treatment 1 and treatment 2, so we will have the mean for each of the groups, right? Or categories or levels. But this can be time consuming, especially when there are lots of categories, like 5 or 10 different plants. So in this case, we have a function with the name of tapply, which is a very useful function to apply a function such as a mean, maximum, median, minimum variance for a subset of vector. Okay, so how this works, so let me remove this. So first of all, I use tapply function. The first argument should be the variable that you want to summarize. So I want to summarize weight. The second option is the grouping variable, which is the group variable. And the third option or the third argument is the mass operation, the function that you want to use. For example, I want to have the mean of weight for each group. Okay, so if I click run, so it gives us the mean of weight for the first group, which is control, which is like this, the second group and the third group. Okay, and so it can be very useful, especially when you have so many groups. And here we can see that the weight of the control group is 5.03, the weight of the mean weight of the treatment 1 is 4.6 and treatment 2 is 5.5. And let's also compare the mean and counts. So how many of the plants are in the first category, how many are in the second category, and how many are in the third category. Again, we can use the tapply function, which is a very useful function, and for the weight group, and now based on the length, which gives us the number for each category. If I click run, so you can see for each experiment we have 10 samples. So if we have 10 samples for control, 10 samples for treatment 1, and 10 samples for treatment 2. So now let's talk about Anova test. So now we have a good idea about this, the data. So we know that the null hypothesis states that all of the means are equal at the population level, right? And the alternative hypothesis states that at least one mean is different. So for this example, our null hypothesis will be the mu for the first group, which is control, equals to the mean of the second group, which is TRT1, and equals to the mean of the third group, which is TRT2. Alternative hypothesis states that at least one of these one of the means is different. Weight of plant. So before running analysis of variance test, it's a good idea to plot the data and compare the distribution of the groups. Okay, so let's create data visualization. And the box plot can be very useful to compare the variation of weights for each group, right? So we can use box plot. So we're gonna have the box plot of weight, but separated by group, okay? And so it creates a box plot like this for 3 different groups. So let's make this a little bit nicer, put a comma, and then you can add a title such as I don't know, plant versus weight, okay, and then click run. So it creates add a title, and we can also add a label for the X and also a label for the Y, and a color for the box plot. So you can instead of typing XLAB here, if you put a comma and then press enter and go to the next line, you can type XLAB equals to, I don't know, plant group, and then comma, go to the next, XYLAB equals to weight, which we don't need to change it, but color, for example, we can use rainbow. Sorry, this should be XLAB rainbow with 3 different colors. And after that, if I select all of these 3 lines and then run, so it creates this 3 box plots. So for the, we can see that for the treatment, it seems that the mean is smaller than the control, and the control is different from the treatment too, but this is at the sample level. Analysis of variance is at the population level, whether they are their mean at the population level is different or not. So now let's run the Anova test that we use AOV command, okay, and then the first argument will be the variable weight, okay. We're gonna see whether the weight is different or not, but for different groups separated by the group. Okay, and that's it. If you click run, it gives us gives us the sum square for the groups and also sum square for the residual, and also we have degree of freedom for the group and degree of freedom for the residuals, right? And we know that we can measure the F statistic using this sum squares of the groups and sum square of the residuals, that F here will be this value, sum square of the groups, right, divided by the degree of freedom, which is 2, and then divide sum square of the residuals divided by the degree of freedom, which is 27. So this is your F statistics, which is 4.84. And using this F statistics, we can make decision whether we can reject null hypothesis or we fail to reject null hypothesis. Okay, but R also can automatically calculate the F statistics and also other derivatives, other useful information. Okay, so if I save the result of Anova test in an object, any object, for example, results, okay, and then click run. So here is the result. If I take a summary of the results, so here we can see that it gives us the F value or F statistic, which is what we already measured, 4.846. And here the probability or p-value is less than 0.05, right? Which shows that this test is significant and is not due to chance. So we can conclude that there is enough evidence that at least one mean is different from other means at the population level. Or in other words, at least one group of plants has significantly different weight or mean of weight from another group of plants. But notice Anova cannot tell us which two groups are different. We need to run post-hoc test, and post-hoc test is used to determine which two groups are statistically different from each other. And probably the most common post-hoc test is Tukey's HST test, and Tukey's HST, or honestly significant difference, compares all of the possible pairs of the groups. Okay, so if I here type post-hoc test, so if I type Tukey's HST and under results of the Anova test and then run, so we can see that all of the possible comparison between treatment 1 and control, treatment 2 and control, and treatment 2 and treatment 1. So which two groups are significantly different from each other? If you look at the p-value, adjusted p-value, this group has p-value less than 0.05. So treatment number 1 and treatment number 2 are significantly different from each other. And but at the 95% confidence level. Okay, so if I also look at the box plot, treatment 1 and treatment 2, they seem that there are very large difference between their mean, but we weren't sure at first. But using the Tukey's HST test, we confirmed that at the population level their mean are different from each other. And this test was at the 95%, the default was 95% confidence level. You can change the confidence level to 0.99 and then run the test. So here at the 99% confidence level, still you can see that these two treatment 1 and treatment 2 are significantly different from each other. And for the 99%, which means that if I repeat this experiment 100 times, in 99 times the difference will be significant. And finally, we can test equality of variance. So we know that one of the assumptions of the Anova was to test the equality of variance, right? So we can use equality of variance. So how we can compare equality of the variance between different groups? Using we can use Bartlett test. Bartlett test for the weight and separated by the group. Okay, and then if I click run, so the null hypothesis in Bartlett test states that all of the variances are equal, and if we get a p-value less than 0.05, we are able to reject the null hypothesis. But here you can see the p-value is not less than 0.05, so we fail to reject the null hypothesis. In other words, all of these samples have equal variance, which is one of the assumptions of the Anova test.